I welcome you again for this course on earthquake resistant design of foundations. And as we discussed in the last lecture, now that we have started already pile foundations, and this is the second lecture on pile foundations. Within the pile foundations, we have started piles for static vertical loads, and as it is discussed in the first lecture on pile foundations, we have covered these parts. We talk about introduction, uses of piles, type of piles, selection of pile type. Then one of the very important topic for static vertical loads, that is pile load capacity in compression, where we talk about static pile load formulae, pile load test, dynamic pile formulae, and correlation with penetration test data. All these so far we have discussed was for the single pile, but as mentioned earlier that piles are used in a group. So, today we are going to talk that when the piles are used in the group, what is the group action of piles, and once we discuss the pile group, then we will talk bit about settlement of piles, and finally one numerical example will be discussed in today's lecture. So, let us talk about group action of piles. When we talk about group action of piles, as said, piles are usually used in a group. This is to ensure that the structural load from a member like a column or a wall lies within the zone of the influence of the foundation. Yeah, it is very important. See that suppose your superstructure is there. From superstructure load will become either column or it could be pier of a bridge. So, what will happen if we do not use a pile group, we use a single pile on the top of this is let us say pile, and the top of it you have this this is a column. So, what will happen? This column may be transferring the load not only to the pile, but the load may get distributed, and this kind of, if you are using a single pile, then it could be a problem. If a single driven pile is used at the foundation, then one cannot be certain that the pile would be located centrally below the foundation elements, because it may move laterally during driving. This is important. So, let us say I have a single column and below column I have pile, but what may happen, let us say initially we have made sure that the center axis of the column and axis of pile is coincide, but when we move install the pile, it may be little bit move, and there could be some eccentricity, or there could be the inclination, and then if you are using a single pile, then it could be not safe. So, the resultant eccentricity of the loading may result in the development of bending stresses in the pile, and pile may fail structurally. So, this is the same thing which we have. Hence, a minimum number of 3 piles is used under a column in a triangular pattern, even the load does not require use of 3 piles. So, it is said that whenever 3 piles will make a form like a tripod. So, you have 3 piles. So, the load is coming from the top, and that so when you use 3 piles, these are 3 piles looks, and how it will look in the plan, it will be like a kind of a triangular. So, the location is here, here and here. So, 3 locations are there. So, in a triangular pattern, so these 3 piles are recommended. Even your load requirement says that 1 pile is enough, but that should not be the case for stability. When more than 3 piles are used, they are so arranged that they are symmetrically with respect to load. So, for example, if I use a pile group 2 by 4 piles, so it will be better in a square pattern or rectangular pattern to use that 4. So, for the symmetrical, you should have the at the corners. So, this one, if you use 5 piles, then 1 more pile should be at the center. So, like that. So, requirement of the minimum of 3 piles is not necessarily applicable to board piles, and for board piles there could be the case, because it may be you are rather than driving, you are boring that. So, in that case it may be 1 may be sometime enough. Continue with that. Now, when we talk about group action of piles, there is a, because when you have piles, a number of piles, they are connected through what is called a slab, which is called pile cap, and pile cap is the cap which connects all the heads of the piles, and the load is transferred to the piles in the group through a reinforced slab called the pile cap, slab on beam called the pile cap. The pile tops are connected together to the pile cap, which helps the pile group act as an integral unit. Now, within the pile group, if your pile cap is not touching to the ground and there is a gap between ground level, this is ground level, and then you could see that this is a clear gap here between the ground and cap, then this is called freestanding pile group. So, freestanding pile group is this one. So, this is the freestanding pile group. If your pile cap is embedded inside the soil or pile cap is fully resting on the soil partially or fully, then in that case this will be called piled foundation which is typically used for embedded foundation pile cap. So, these are the terminology typically used in the literature. Continue with that. Now, we come to the ultimate load carrying capacity of pile group, and ultimate load carrying capacity of a pile group is judged by a factor called group efficiency, and this group efficiency eta is given by this relation QUG divided by NQU, where QUG is nothing but ultimate load capacity of the pile group, N is the number of piles in the group, while QU is the load capacity of a single pile or a one pile. So, the pile group efficiency eta sorry, this is not N, this is eta, depends mainly on the spacing between piles, the type of the soil in which the piles are installed, and the manner of pile installation, that is driven board constants to etc. So, the value of eta, which is the efficiency of the pile, depends on many factors including type of soil and the manner in which type is installed, and most importantly this depends is a function of, if other things are constant, spacing in between piles. So, spacing between piles makes a lot of difference on the efficiency, and we are going to discuss in details spacing between piles. Distribution of soil during installation of piles and overlap of stresses between may cause the group efficiency become less than the sum of the individual capacity. Normally, the value of eta, that is the group efficiency, is less than 1, especially when the spacing between piles is not very not large. So, generally for small spacing between piles eta is less than 1, but if you increase the spacing between piles, that means you have, then it will may act like individual piles and the group efficiency may be almost reaching to approaches to unity. But naturally this eta is 1 or more than 1 is desired, but what happens if you keep higher spacing between the piles, then you will require a large size of pile cap. So, that is not going to be economical. So, there is an optimum value of eta and there is optimum spacing between piles which need to be decided according to the economy of the projects and the space. So, simply to increase the value of eta, if we keep increasing the spacing between piles, that is going to be uneconomical. So, now continue with this, that ultimate load capacity of the pile groups, in this figure there are two cases. One is called point bearing piles, where the most of the load is transferred through the point bearing action, and another is friction piles. In both the cases a single pile and pile group are compared. So, you could see for point bearing action Q is the load coming from the top of the pile and it is transferred through the point bearing action, and maximum load will be transferred to the just below the pile tip. Okay. While you have in pile group again same Q is the load carried by a single pile. So, you have Q for all the 3 piles, and then the stresses will be transferred like this. So, you could see it was very maximum here, this is not the case here, rather the difference have between minimum and maximum have reduced, and that means through point bearing action the load is transferred. While in case of friction piles you have a pressure bulb for a single pile here, and again for pile group this there are overlapping between like that here 3 pressure bulbs are there for each single pile and they are overlapping each other. So, in this case point bearing action through this one, and here the settlement because will going to be higher for the group piles. So, now continue with this ultimate load capacity of the pile groups. In driven piles where the soils around the piles get densified as a loose to medium sand, eta may be even more than 1, okay. And the reason being due to the pile group, because if you use a single pile rather than a single pile when you use in a group, and for using the piles in a group, if you need to put like that driving the piles so what will happen, your soil get densified, and once soil get densified it may result eta value of eta more than 1. In such cases pile group tends to behave like a block or like an equivalent single pile. Larger spacing may necessitate a bigger pile cap, which is uneconomical. So, this is a thing which we already discussed. If you increase the spacing between piles, the value of eta or group efficiency may increase, that is good. However, at the same time it will require large size of pile cap, and that may be uneconomical. So, simply we cannot have that, let us say keep more spacing, so you get higher value of eta, rather than will be an optimum value of eta, optimum value of spacing between piles, which provide you whatever eta you get, whether it is less than 1 or more than 1. So, now what is our code suggests, there is code IS 2911 part 1, and this letter so far is 1979 version. So, the code suggests something regarding the minimum spacing of piles, and what is recommended, that minimum recommends a minimum spacing of 2.5 times the diameter for point bearing piles. Minimum spacing is for end bearing piles, this spacing S should be minimum should be 2.5, that means S should be more than 2.5 D for the first case. But if you have friction pile, then spacing should be more, that should means S should be more than 3 times of D. But for in the loose sand deposit, S minimum spacing can be 2 D. So, in any case spacing center to center spacing between two piles for any type of soil is required is 2 D, and 2 D center to center spacing means there will be clear spacing of 1 D only. So, 1 D clear spacing is required between two piles. So, this is the recommendation of the code, IS code also. So, and then continue with this, the ultimate load capacity of the pile groups could be due to the failure of pile groups, may be due to block failure or individual pile failure. So, when you have the block failure, it is normally for spacing less than 2 to 3 times pile diameter. But if you use the larger spacing between the piles, then the pile group may fail as a block failure. That means, this piles rather than failing individual piles, there could be the, that means the complete block has been failed. Next is settlement of a pile group. This is the last theory part of this for vertical load carrying capacity. So, as we said that there are two criteria for designing pile foundations, which is the same as other type of foundation. One criteria, there should be adequate bearing capacity, that means factor of safety should be enough. The second is settlement should be within the permissible load, and normally the settlement in a group of pile is more than the settlement of single pile, even when the load on the single pile and the load on each pile of the pile group are the same. That means, one side you have a pile group, another side you have a single pile. The load applied on pile group is n number of piles multiplied by that load on the single pile. So, that is the unity, but still the settlement of the pile group is expected to be more than the, particularly for the sands, more than the settlement of a single pile. It is because the zone of influence of a pile group is much deeper than that of a single pile. So, this was regarding the settlement of a pile group, and finally, we come up to what is the allowable load on a pile group. When we talk about allowable load, naturally as for the shallow foundation, the same thing is for pile foundation. This will be governed by based on the two criteria which we have this one. Under vertical load is first determined on the basis of shear failure criteria, then the settlement of the pile group under this load is then computed, and the settlement should not exceed the permissible settlement, and the allowable load on this pile group is the smaller of the values calculated either on the basis of the shear failure criteria and the settlement criteria. So, you check the load you find using shear failure criteria as well as find the load using the settlement criteria, and out of these two values the minimum or smaller one will be the allowable load on a pile group. Now, let us discuss one numerical example which talks about the pile capacity, and in this example what is done, the question given is here, assuming a factor of safety equal to 3, determine the allowable pile load capacity of a 40 centimeter diameter driven concrete pile which is shown in figure. Here in this figure you could see that in this figure you have 3 layers of soil A, B, C, right. The thickness of A layer is 2 meter, B is 4 meter and the C is 6 meter. The soil properties are listed here. A is a loose sand and its unit weight is 16 kilonewton per meter cube and phi equal to 30 degree. While B is soft clay with saturated unit weight of 18 kilonewton per meter cube and Cu 15 kilonewton per meter square. While C is dense sand with gamma saturated 20 kilonewton per meter cube and phi equal to 40 degree. And you need to understand that A between A and B, A is the water table is located between the interface of A and B. So, this is the location of water table. So, means below A layer both layer B and C are the saturated layers, and further data is given. This is the table which we have discussed in the theory, that for different pile material for steel, concrete and timber the value of delta and value of K is listed here. What data is given to you? For determination of skin resistance in sand, values of K and delta are given in table as discussed. Also it shall be the sand maximum unit friction is should not exceed 100 kPa, and while for unit bearing resistance cannot exceed 11,000 kPa. Further, for clay stratum adhesion factor is alpha is given, and for dense sand stratum bearing capacity factor NQ is given 150. So, with using all these data we do start our calculation. So, what is the first of all, as you know, the total ultimate load of pile Qu will be skin friction Qf plus point bearing resistance. However, to calculate skin friction we need to go layer by layer, because skin friction for A, layer B, layer C will be different. So, what we do? We find skin friction resistance for A, B, C and then combine, and then we find point bearing load, and then total Qu equal to Qf plus Qpu. So, this is here. So, this is total load, ultimate load. Now, let us first work on the first component Qf, and for the skin friction capacity Qu, this is determined layer by layer. So, first for the loose sand stratum, for concrete pile delta is 0.755, which is given in this table. So, this 0.75 pi is coming from this table, and for this is loose sand. So, K will be 1. Okay. So, 0.75 phi is 30 degree. So, as a result delta comes out to 22.5 degree and K is 1 for loose sand. Now, thickness of this stratum, first stratum is only 2 meter, while diameter of the pile is given in the question 0.4 meter. The diameter of the pile is 40 centimeter. So, D in this case is D given is 40 centimeter, which is equal to 0.4 meter. So, L by D ratio for this layer A thickness is 2 meter divided by 0.4 gives you 5, and this L by this is less than the critical value, because L by D it can up to 15 this it is linearly increasing. So, what you have, the sigma bar increases linearly with the depth, and average value of sigma average from the first 2 meter layer. So, from here, so you find the average will be here it is 0, it is the maximum value. So, average will be half of the value at the bottom. At the base, what is the value? Gamma T into L, where 16 into 2. So, you have ultimately you get 16 kilonewton per meter square sigma average for this layer, and unique skin friction resistance Fs average is sigma average bar into K into 10 delta. You just put the numbers, then ultimately you get 6.627 kilonewton per meter square, and you need to make sure that this value is less than 100 kPa. This is okay. So, we get this value for the first layer. The unit skin friction resistance is 6.62, and with this you can find the skin friction resistance total skin friction resistance Qf1 Fs average into As. So, that means just multiply with the area of the surface area of the pile, pi into 0.4 the diameter, and 2 is the depth, the thickness of that. So, ultimately you end up for the first layer load is 16.66 kilonewton. Similarly, for the second layer, but for the second layer is not consist of the sand, rather it is clay. So, for the clay Fs average will be found out from using this equation here. Fs average for the second layer will be calculated here, what is called alpha into Cu. Fs average will be alpha is given, Cu is given, Fs average is basically in this case alpha into Cu. Alpha value is given already 1, Cu is 15. So, just we put A as the area is pi into d, and then this 0.4 meter is this, actually this is 4 meter, this should not be, sorry, this is wrong, this is wrongly printed, this should be 4 meter, and so this is 0.4 into 4, so 75.40 kilonewton. Then for the third layer, which is loose sand stratum, due to the arching effect, depth of clay stratum is not required to consider and determine critical length of pile. What is arching effect? I can explain to you. See, you have the loose sand in layer A, layer B you have the saturated clay, and then you have dense sand. So, between two sandy layers you get a clay layers. So, the clay layer will provide an arching effect, and the length, critical length of the third layer, that is C layer, should be counted from the top of it here, not from the ground level. If in between these two sand layers, if you would have another sand layer, then the length, critical length for critical depth of the pile would be counted from the top ground level. So, in this case again 6 meter divided by 0.4, 0.4 is what is 0.4, 0.4 is the diameter of the pile, which is less than 15, and the last layer is for dense sand. So, it is going it is less than 20 still. So, it is fine, that means the sigma bar will increase continuously up to the pile tip. So, sigma bar increases linearly with the depth. So, sigma bar at the top of the sand stratum, 16 into 2 the first layer, and this is the contribution coming from the clay, where 18 minus 18 is the unit weight of the clay and 4 is the thickness. So, at the top of the sand stratum 64.76, while at the bottom of this layer, that is at the tip of the pile, 64.76 plus 20 minus 9.81, and 6 meter is the thickness of that layer. So, you end up in the pile tip this value, and the average value for this layer comes out to be 95.33, and with using this average we find Fs average. Now, delta is 0.75 pi phi, so 30 degree, because phi is 40 degree now, and k for dense sand is 2, earlier it was 1. So, you end up in Fs average values, which is 90 ultimately 110.07, and this is being more than 100 kilonewton per meter square. So, Fs average used in the calculation is only 100 kPa, and for this third layer Fs using Fs average 100 kilonewton per meter square, we find its load carrying capacity Fs average into As, where As is 0.4 into 6 meter. So, you got 754 kilonewton, and then we end up add all these three total skin friction resistance for all three layers, Qf equal to Qf1 plus Qf2 plus Qf3, and ultimately you get this number 846.07 kilonewton as a total skin friction resistance capacity. Now, we work out on point load capacity, which is QPU. So, when we talk about point load capacity, sigma bar at the tip of the pile is 125.9 kilonewton per meter square as determined here, and NQ is already given 150. So, QPU value will be sigma bar into NQ, which is 18,885. However, because this value is more than 11,000, which is the limiting values. So, QPU is find out as 11,000 kilonewton per meter square. This will be used in the calculation, and the ultimate point bearing resistance QPU into AB. So, you get it here 1382.3 kilonewton, and this is point bearing resistance. Then allowable pile load capacity QU, this will be QA. Load pile capacity QA can be determined. First, you find the value of QU, which is QF plus QPU. So, the total ultimate pile load capacity is 2228.37 kilonewton, and when we divide a factor of safety 3, then you get 742.79 kilonewton, which is basically allowable load for the piles, and this is your answer for this. So, we can allow for the given diameter of the pile 0.4 meter given strata, the maximum load the pile can carry is about 700 kilonewton. So, that is the answer here, and this will this is coming with a factor of safety 3. So, this completes the numerical example. whatever we have discussed in the first lecture and second lecture on pile foundations is coming from these two references. One is mostly Prakash and another a book by Ranjan and Rao. So, mostly it is from the second references, and I certainly acknowledge that this is like whatever we have discussed, theory part and other things are from there. So, today and in the last lecture we have, that is 2 lectures we have covered so far on pile foundations, and both these lectures we have discussed static pile load capacity in vertical direction, or you can say pile load capacity in compression for vertical loads, and we have exclusively considered only static load. So far no lateral load is considered. However, we have discussed for single pile as well as for pile group. For single pile we have discussed this how to find the pile load capacity, so using static pile load formulae, dynamic pile load formulae, penetration test data as well as institute test data, and then we talk about group efficiency, and then we also finally discuss one numerical example. So, with this this is on the for vertical load carrying capacity, this is over. In the next lectures we are going to talk about very important part on pile foundation, that is called lateral load on piles. So, how to go for the lateral load on piles, and I think that is the most important topic for this earthquake resistant design of foundations. So, we will discuss that on the lateral load on piles in the next lecture. With this I finish it here today. Thank you very much for your kind attention. Thanks.